Good evening, everybody. So, who's glad this is not on Zoom? Yeah. So good to see a lot of old faces and some new faces here at this event. So, our speaker tonight, Professor Zanna, is one of the 4 coordinators of one of the 2 programs we're currently running, which we've been running in person, also in hybrid mode, so streaming to the outside world. So this is our new way of doing things. We'll see how far it lasts. But this is a program on machine learning and climate science. So we're always sort of pushing the frontiers of the kind of things that we do here. And I think you can see it all on the screen here. Professor Zanna is a professor of mathematics and atmosphere/ocean science. That's a pretty cool title. In Department of Mathematics at the Courant Institute, one of the top mathematics institutes in the world. And in there is also a Center for Data Science. So there's mathematics, physics, computer science, fluid dynamics. There's everything in the work that she does. I always tell you we only bring you the very best experts here for these talks, and Professor Zanna is an expert on climate dynamics. Her PhD is from Harvard University, 2009, in climate dynamics, and she spent quite a number of years as faculty member at Oxford University before moving back to the US, New York City Courant Institute. And among her many awards, there's a very recent one, 2020 Nicholas Fofonoff Award from the American Meteorological Society for exceptional creativity in the development and application of new concepts in ocean and climate dynamics. So that's what she's going to tell us about tonight, and I'm very grateful for her excellent running of the program here and for giving this talk for us tonight. So welcome and thank you.
Thank you. Thank you very much for the introduction, and thank you everybody for being here. It is always a little bit weird to be back in person. So I gave my first science talk here at KITP about 3 weeks ago when our program started. And it was my first science talk in front of an audience since February 2020. So I wasn't sure if I knew how to do it again when I'm not on Zoom in 2D. So now it's my also first public talk since 2019 in person. So I've done a lot of those on Zoom. So again, let's see how I do. So I'm a trained physicist, as Mark mentioned. So basically got a PhD, in climate science, but really kind of applied physics. And really what motivates my work is actually understanding how the climate system works, and especially how the oceans work. And so here what you see is a numerical simulation. So it's a computer simulation that tries to mimic what the oceans are doing. And so what you can see, it's complicated, right? It's a lot of features that wobbles around. There's a lot of things happening here. And so a lot of the features that you see here in that numerical simulation, it's a lot of physical nonlinear interaction, quite chaotic, that moves things around. You can see a lot of waves as well that propagate everywhere. So really understanding the ocean means understanding the physics of it, understanding how the fluids move around, understanding how it absorbs, heat and carbon. So really have some thermodynamics property of the ocean. So really big, component of the climate system. And so that's what I'm going to talk to you about tonight. And so I hope you're excited about the topic as much as I am. And so I'll tell you a little bit about some of the challenges that we face in ocean and climate dynamics, how we try, to come up with new methods and new ideas by bringing physics, math, computer science, and machine learning, and hopefully take you through a little bit of a roller coasters of what we know, what we don't know, and what we still need to address. So again, a little bit of a roadmap. I'm going to tell you a little bit why the oceans matter, and what's their role in the climate system. And I'm going to talk to you about 3 challenges, and they're all kind of intertwined. They're not really separated. One of them is, how do we quantify that the oceans have been changing, and how they've been changing through our evolving climate. Everything is about understanding in our field, right? I'm a physicist. I want to understand how things work. So after we quantify them, we need to be able to understand what's happening, why they're changing, what's going on and will that change continue? Third one is predicting. And that's kind of the beauty of physics is we have governing laws, we have equations, and they tell us when we see something today, we can try to figure out what's going to happen tomorrow, what's going to happen in a week, in a year, in a decade. And so coming up with ways to make better predictions is a pretty important topic for us, right? Obviously, we want to understand how the climate is going to change. How should we adapt, or how should we make better decisions to avoid adapting too much to how the climate will be changing? And of course, it's an exciting year. Nobel Prize of Physics, two of them, Subhiro Manabe and Klaus Hasselmann, are two climate scientists, right? So Manabe basically, to some extent, created one of the first climate models by starting with very simple theory to explain how the climate system responds to changing CO2 emission, to changing carbon dioxide emissions, and was able to predict, how those changes will happen and kind of create the first climate model to make those predictions. And Klaus Hasselmann, also, a prize for climate physics to some extent, and he created the first simple model to explain how the ocean will actually respond to weather. And so it was really a fundamental change in the way we understood how the ocean works on shortish timescale, and also came up with ways to quantify how much the changes come from what we call natural variability, right? Things are always changing. We don't need to push them to change, right? The weather is changing, every day. It's changing. Sometimes it's not our fault. But as we put more carbon dioxide in the atmosphere, we also create additional changes. And so we came up with methods that actually try to separate how much comes from nature, without any external forcing, and how much come from forced changes that, again, come from adding emissions. And so it's been an exciting year, right? 2 Nobel Prize of Physics, being climate science. So that's been a great year, in addition to, being back in person. So I'm going to give you a little bit of a prelude, and that's the way I think about, the work when I approach it. And it's kind of 3 quotes. So the first one is from a statistician, George Box, that said the most that can be expected from any model is that it can supply a useful approximation to reality. All models are wrong. Some models are useful. And I think this is a very important concept. Is like everything I want to tell you about, it's kind of a model, and that means it's imperfect. And so it's good, but up to a certain point. And they all are imperfect. Second one from Samuel Carlin, which is, you can think about it as conceptual model. The purpose of model is not to feed the data, but to sharpen the question. And here we're coming up to the understanding part. We try to come up with simple models, and that means simple explanations, to try to explain certain phenomena, but then rethinking those phenomena, and then again pushing the envelope forward. And I really love those quotes that really tries to tackle the way we think about the problem. And the last one from Paul Anderson was basically a science fiction writer say, I haven't yet seen any problem, however complicated, which when looked at in the right way, did not still become more complicated. And that's kind of the way I think about the climate system, right? Every time we think something is complicated, then you look at it even more, and it's even more complicated. And it's kind of, here's a picture of water vapor in the atmosphere. So, you can see weather system, and it's very complicated. It's multi-scale, moves around all the time. I really love this quote. It really kind of, captures the essence of it. So, quantifying, but up to a certain point, everything is going to be an approximation. We're not trying to find a perfect answer, but we're really trying to push the boundary of understanding. And at the end, it is complicated, and there's still a lot of work to do. So another quote, Arthur Clarke, which, how inappropriate to call this planet Earth when it is quite clearly ocean. And so this is a satellite image, right, of our planet, our beautiful planet, where you can see it's basically mostly oceans, right? So here we can see the Pacific Ocean. Of course, on top of it, we can see a lot of clouds, but the surface of the ocean basically covers 70% of the planet, right? So this is a pretty big and vast system. Now, if we think a little bit about numbers, right? So we have the atmosphere, kind of a height of about 50 kilometers. The ocean average depth is about 4 kilometers. And I'll give you a few numbers. The top 3 meters of the ocean contains as much heat as the whole of the atmosphere, right? So only 4 kilometers deep. If you dive in the ocean 3 meters, you have as much heat in the top 3 meters of the ocean than the whole of the atmosphere. The top 50 meters contains as much carbon as the whole of the atmosphere. So again, even though we emit a lot of carbon, a lot of that ends up in the ocean. But the second thing that the ocean does is it does transport a lot of that heat, a lot of that carbon, the ocean is also salty, so a lot of that salt, it moves it around. So that means it transports all those property all around the world on various, time scale. So it has this kind of, beautiful property that is going to take stuff up and then it's going to start moving them around. And that's the fluid dynamic part of it. So it's a very complex system. So now, how do we observe the ocean? So, and just to be clear, I am not an observationalist, so I do theory and models, but it's very important to understand how we actually measure changes in the ocean. So obviously, the further back in time you go, the less observations you have, because, there were no tools to do that. But a lot of information of how much the surface of the ocean has changed came from basically ships going, between continents. And so aboard the ships, they had basically thermometers to actually measure the surface temperature of the ocean. So how warm the surface of the ocean was. And you can see actually the ship tracks, right, between the continents going back in time. And so this is just the number of observations we have going back 150 years. It's just telling you how many data points we've got. And so some places are completely deprived of information, while some places where, again, you had ships between the different continents actually moving stuff around, you can see a lot more observations. Some places have very long record. So that's how we measure sea level. It's tide gauges. So basically, all along the coast, we have little gauges that actually measures how much water there is in a net. And so this is a tide gauge at New York City, which is where I live. And actually, the record go back further in time, but you can start from the mid-40s, and what you can see is that the sea level is going up, right? And this is a clear measurement. There's kind of no doubt about it. Sea level has been going up, and you can basically find those records all along the coast, all around the world. You can see those tide gauges, and this is the signature that you will see. Sea level has been going up. Technology is amazing. So now we actually get a lot more information. So all those things were quite sparse. We only have a few data points here and there. Now with satellite imagery, then this is a completely different world. So we have satellites basically going around the planet. And what they do is they actually measure the ups and downs of the ocean. So they measure the height of the ocean, how much it moves. And this is the movie that you see here. So what they do is they send a radar pulse. It's going to bounce back from the surface and measure that distance. And so this is what we call altimetry. And so those movies that you see here is basically the ups and downs of the ocean. And so again, you can see a few interesting features, right? A lot of little wobbles over here. And so again, that's usually the part of the system that is very hard to predict. It's very chaotic. It's very nonlinear, called turbulence. You can see a lot of those kind of, warm and cold pulses almost over here, right? You can see those kind of very long stuff going on here. And it's El Nino, which you might have heard of. So it's a climate phenomenon that is happening, every 2 to 7 years on average. And it's a completely natural phenomenon. And you have waves propagating around the equator, and you have warming and cooling on those periods. And we can observe all of that from satellite, and it's global. But the problem, of course, it only started in the 90s. So we have a short record of those global pictures. In the interior of the ocean, that's harder, right? So all I showed you right now was what do we measure at the surface. And the surface is always easier. But the ocean is deep, pressure is high, and it's harder to get measurements down there. And so that's, again, just to show you how many observations we have over time. So that's, 2008. All the dots that you see are basically places where we have measurements in the interior of the ocean. If you go to the 1950s, well, you can see it started to be pretty depleted, right? There's very little measurement. That means we know very little about what happened in the interior of the ocean. If you go to the beginning of the 20th century, well, there are only a few spots where we have observation in the interior of the ocean. So it's a big challenge for us, right? Actually taking those measurements in the interior of the ocean and understanding how it has changed over time. We're getting clever, obviously, with time. And so we have better measurements now. We have floats. We have, basically almost 4,000 of them. This is basically a map that I downloaded last night. So those float down here, they basically kind of dive 2 kilometers deep in the ocean. They take some measurement, pop back up, transmit their position and some information to satellites. And we get a lot of those floats they basically drift around the ocean. And they take a bunch of measurements diving up and down and giving us some measurements of the temperature. Those floats can't go underneath the ice. So some scientists came up with some ways to actually put it on those guys. And so what those guys do is they actually dive underneath the ice, and those are the paths that they do around Antarctica, all around the ice in places where it's very hard to actually take measurements. And so you put those things on top of their head, and they go up and down, and they actually take profiles, and they give information that we wouldn't have otherwise. So we're becoming creative in the way we kind of take measurements. But it's helpful because, I mean, we're gaining more and more information about how the planet has been changing. But still, right, it's vast, it's been under-observed for the most part, and it's multi-scale and constantly changing, right? So we have all those turbulence features that move around, we have a lot of large-scale waves, and so, you know, trying to understand how the ocean has been changing has been challenging. So a lot of our work has been trying to, you know, bring physics together with some observations. And so what we've done is we try to think about how the ocean works. And what we know about the ocean is it's going to absorb heat at the surface and start basically carrying it down via the ocean circulation. And so we came up with a simple kind of mathematical and physical model that tried to capture that by taking observation at the sea surface of the ocean and reconstructing how much heat must have entered the ocean based on the physics that we know. And so we basically did a reconstruction of ocean warming, so how much the ocean has warmed in the past 150 years, actually without having, or at least with very low measurements in the interior, only by using basic physical principle and simple math and some observation at the surface. What you can see obviously is that, you know, the planet is warming when it gets, you know, yellower. That's where the ocean warms more. And it enters in two big places, which are usually the North Atlantic and the Southern Ocean down here. Those are basically the lungs of the climate system. That's the places where you're going to absorb most of the heat and the carbon and burying it at depth. And so that's, you know, some of the work that we do is kind of trying to bring knowledge of physics to understand how the planet has changed. So now, why is it useful, right? So somebody could say, why is it useful? Because understanding how much the ocean warms means that we can get an estimate of how much or why sea level goes up. As you know, as water warms, it expands. Right? It's kind of basic physics principle. And so by using those kind of, you know, data sets, we were able to reconstruct how much sea level has been going up due to the warming of the planet, or due to the warming of the ocean. And sadly, obviously, what we can see is, you know, sea level has been going up and continues to go up and accelerates over time. So again, bringing those ideas of you know, basic physics with some observations, try to quantify changes. So, you know, I told you about the past, and that's kind of a little bit same way to show you the movie that I showed you before. This is how the ocean warms over time. So 1971, then moving in time, you know, 1981, and so on, up to present. And here, what I'm showing you is the future. The future comes from climate models. And what you can see is, again, getting yellower and yellower, meaning that as we put more carbon dioxide into the atmosphere, planet is warming, a lot of that heat is being absorbed by the ocean. So more than 90% of the excess energy that we put in the climate system ends up in the ocean. And that's why we can expect our oceans to warm. And that means more sea level. So a little bit of, you know, understanding how the heat is being moved around the ocean is also pretty important because it tells us how the fluid is changing over time. And so here, what I'm showing you is how much warming has happened over 60 years. So what we're doing here is we basically, you know, summing up from the surface of the planet to the bottom and checking how much warming has happened. So when it's red, that means that the planet is warming. The redder it gets, the more warming you get in those regions. But you can see that there are some spots where it's cooling actually, right? So the blue spot over here means that the ocean is cooling, while in some places it's actually warming. Some places it's warming a lot more. So one could ask the question, why is that, right? Why is it not warming everywhere as we're warming the planet? And one big reason is the ocean circulation is moving the heat around. And in some places it's gonna carry it and then get stuck there. It's gonna warm faster. And in other places, it's gonna cool it down. But again, we're still stuck with the same problem. We have not enough observation to actually figure out how the fluid is moving and how the planet is changing. So again, bringing simple theory actually, that was my first PhD student a few years ago. We came up with a simple theory of how the ocean absorbs heat and carbon. and using that as a proxy to understand how circulation is changing. And we're able to separate this pattern of warming in two pieces. One piece, which is what we call the passive uptake. And you can think about it as you're at the surface of the planet and you put some dye, and the dye is basically the excess energy that comes from, us emitting more greenhouse gases. And that's going to passively be taken up by the ocean. A little bit like dye, right? So you put some dye, in your cup, and it's slowly going to mix, right? And kind of get passively moved around the ocean. And so that's one component. And then the residual, so if I take this minus this component, that is not the simple dye penetrating the ocean, this is a signature of where the ocean circulation has been changing. So it's an indirect way to measure how the fluid has been accelerating or decelerating due to climate change. And so again, some places where the ocean has decelerated does mean that some places are cooling while others are warming. So that shows you the complexity of the ocean, right? It's this big, vast blob that can take up a lot of heat and carbon, but it also moves it around. And then as you change its temperature, it's also changing its circulation. So that means it's changing the way the fluid is being moved around. So those are kind of simple signature to understand, the processes. Now, again, if we take climate models, that means numerical simulation of what the planet would look like. So that was the past, that was observations. That's the future, if we continue to emit at the rate we've been emitting. And now again, without telling you more, there are no more red spots anymore. Now, there are no places where the ocean is not warming. And again, the more you warm, water expands, sea level goes up. And so in many places, like around the US East Coast, for example, sea level will actually go up much faster. Question? Yes, please. Oh, yeah, please go ahead. Oh, yeah.
Wait, hang on, Robert. So, sorry, maybe I'm missing me. So why are there blue spots?
So what happened is that as, as some of the heat enters the ocean and some of the winds are changing, it's actually changing the transport of heat from low latitude to high latitude. So in general, you're going to transport warm water towards high latitude. And that's what the ocean circulation does. When that decelerates, then that means you're actually not transporting as much water, warm water, up to the high latitude. So you're going to end up with basically a colder spot up there as a signature of your ocean circulation changing. But in the future, even if the ocean circulation is changing, you're taking up so much heat that the ocean is going to warm no matter what. Please ask questions. A lot more fun with questions.
Yes, perfect timing. I read an article today from November Scientific American on how water vapor affects the intensity of storms, more and warming of the atmosphere, even more so than carbon dioxide.
Yeah, so that's a great question. So basically, what's happening is storms are fueled by surface temperatures, right? So basically, it's a little bit of the fuel that's gonna make them work. And so as we're warming the surface of the planet, there's more water vapor that basically kind of enters the atmosphere, and so you're fueling those storms even more. So it's really this very delicate balance between the oceans and atmosphere. Indeed, yes.
Laura, question I had is, what you hear in the paper is the ocean is rising because of the melt.
Yes.
But you haven't said that.
Yes, that's a great point. Absolutely, yes. Sorry, and I should have, because it's right here. Actually, it's on that part. Yeah.
But we'll come back.
Yeah, you're absolutely right. So I only mentioned the part about the ocean warming because it's it directly translates to our ocean warming. But yes, land ice and groundwater is actually contributing to basically 2/3 of the sea level. Over the earlier period. Right now, we have about 1/3 that comes from ocean warming, 2/3 that comes from melting of ice, of land ice. Oh yes, sorry, this is in millimeter, right? So basically between here and here, we have about 40 centimeter sea level rise. 2/3 of that is land ice melting. Thanks, sorry about that, yeah.
On the last slide, we had to do with North and South America. Now, yes, you see there at the top, all of the heat seems to be between North and South America and Europe and Africa. Now, those used to be together, a long time ago. And isn't it curious that where they separated between between where they separated that you've got all this heat? Could some of that heat be coming from inside the Earth?
Oh yeah, that's a great question. So, I mean, you know, in terms of the numbers that we have, geothermal heating is actually much, much, much weaker than the amount of heat we get. Most of that band of extra heat is actually a physical principle that we understand quite well. Is we have wind blowing in this direction, and that creates a net transport northward. And so there's a big accumulation of heat all around here. Yeah, so that's very much driven by the wind.
So how do you go from the lower right-hand picture to the future on the next graph?
Yeah. So all of this, yes,
How does it, because you have cooling areas there, and then all of a sudden it leaps into the future on the next graph,
Yeah.
2011 to 2060.
Indeed. So here it's a climate simulation now. So we're not observing the planet anymore like we did here. Here what we're doing is we're putting the equations of motion into a computer, and we're solving those equations. And so the assumption we need to make is how much emissions we're going to put into the atmosphere over the next, in this case, 50 years. And so that's a pure simulation. That's what we call a projection, a climate projections, in which we impose a scenario of how much carbon dioxide we're going to put in the atmosphere. And then we run our climate simulations that include the oceans, the atmosphere, the ice, and we run that forward in time and make this prediction.
One obvious feature of that bottom picture, of course, is this tremendous concentration of the high heating in the Atlantic relative to the rest of the world. Is there a simple understanding of why that is?
Yeah, so we have a very strong circulation going on here, and so we have a lot of sinking at high latitude. So those places actually have what we call a weak stratification, meaning it's a lot easier for heat to enter the high latitude of the North Atlantic. And it's also a lot easier to enter the Southern Ocean. And so what happened is that a lot of that heat is being basically kind of concentrated in the basin. And as the circulation is changing, as the circulation weakens, then the heat piles up, basically, has nowhere to go. And it keeps basically intensifying itself because it's there, keeps being warmed, and it gets stuck there. Oh, this is great.
Yeah, I almost there.
So are you saying it's the size of the ocean that makes the difference, and that it makes it easier to heat up in a smaller area than the Pacific, for example?
That's an absolutely amazing question. And that's one of the conundrums, actually. Why is the circulation in the Atlantic different than the Pacific? So is it because of the size of the basin? So yeah, it's easier to warm. But actually the circulation is quite different. And that's one of the big questions that we have. Why is there sinking here and not in the Pacific? And so there are a few hypotheses out there. One of them is part of the Atlantic is actually saltier because of the Mediterranean. And so that changed the structure of the ocean. Other ideas are that the Atlantic extended further north. That means it's colder, and that's easier for water to sink. So right now we have multiple hypotheses, but actually none of them are satisfactory. So that's one of the big open questions. Why is the Atlantic circulation different than Pacific? Great question, yeah.
So these projections due to thermal transport equations fed by the atmospheric warming from greenhouse gases, et cetera. Is that what it is?
Yes. So in those projections, what we do in the climate model is that we make an assumption. We say, okay, we're going to assume that we continue emitting at a certain rate, CO2. And as we emit that CO2, right, so basically it's a greenhouse gas. That means the temperature is going to go up. But now the ocean has a massive heat capacity compared to the atmosphere. That means that the atmosphere does not remember that heat. More than 90% of that heat is going to be absorbed by the ocean. And that's basically going to warm the ocean, and that's going to make the temperature go up. Yes.
I had a question. There's some purple areas sort of extending from the Farallones east and then southeast of New Zealand. What are those?
Okay, so we're talking about here?
On the lower.
Oh, lower part. Yeah, I mean, it's all quite red, right? So in general, it warms a lot. Now, because the ocean always changes, the rate of warming or lack of warming will always depend on the ocean circulation at that spot. That's a big signature of it. The second thing is usually, as we put CO2 into the atmosphere, it mixes very quickly, but then the temperature itself is not very well mixed. That means that some places will feel the stronger forcing than others. So we always have that complication of the surface warming that we impose due to greenhouse gases is non-uniform. And then the ocean is going to move all that stuff around, and then the ocean is also changing. So you never get something that is uniform.
Okay, I think we're going to.
That's great.
Please proceed.
Thank you. Yeah, I love being back in person. This is part of the fun. Yes, thank you, everyone. Okay, so now you actually raised all the point that I wanted to bring up, which is we make projections, and we need to make some assumptions about how much carbon we're going to put in the atmosphere. That's what we call usually a scenario in climate. Call that an emission scenario. How much greenhouse gases we're going to put in the atmosphere, and then we run our simulations with it. Now we have many simulations because different modeling centers create their own climate models, even though we have the same equations. I'll show you it's actually not very simple to solve them. And that means that even if you give two modeling centers the same pathways over the next 50 years of how much emissions we're going to make, those models are actually going to give you different projections. So for a given emission scenario, that's going to be the red thing that we see here. Let's say it's just a given rate at which we're going to emit starting in 2000 all the way to 2100, so basically at the end of the century. And all the shading that you see is basically projections from different climate models. Even though they feel exactly the same amount of greenhouse gases and the same emissions, the models can give you a projection of sea level in this case and that's only from the thermal expansion, so how much warming you get. So it can be something like 22 centimeters to 38. Big difference, right? I mean, if you live at a place and you have a projection and an uncertainty that is that big, something you want to think about. So why our climate model actually get the trend right on average, and they do a really good job at many things, but yet they will give you something uncertain. And one of the reasons is we need to solve those crazy equations, right? And I mean, we love them. They're amazing equations. What they are is the first one on top here is the fluids equation. So that's really the non-linearity of the fluid, and it's very complicated, for the oceans and atmosphere. First, because we are on a rotating planet that makes everything always more complicated. And so, you have those kind of very complicated equations that you have to solve. You need to solve for, the continuity equation, the fact that you conserve mass to some extent. Then more thermodynamics, right? The fact that density is related to temperature, salt, and pressure in the ocean. So that will change the density, right? So if you have a warm ocean or cold ocean or saltier ocean or less salty ocean, you will change the density. Then, of course, as we mentioned, we have heat. That's temperature, and that's salt because the ocean is salty. So we need to solve those quite complicated nonlinear equations. That's impossible to solve that by hand, obviously, right? So we need to put them in the computer. And so again, and I'm only showing you the oceans, right? You will need to have, for the atmospheric chemistry, and then all the biogeochemistry in the ocean, and so on and so forth. So if you were taking those equations and apply them to each air and water parcel, and let's assume we just have basically 1 meter cube of seawater that evolves independently, you would end up with 10 to the 28 equations to solve just for the ocean. So it's literally impossible, right? This is a massive amount of equation that we need to put in the computer, and it's absolutely impossible. So what we do in the computer is we kind of break it into pieces in a grid, and then we're going to solve those equations at every one of those grid points here. But those grid points are not 1 meter cube as I'm showing you here. In general, they are 100 kilometer by 100 kilometer resolution. And it's like massive, and I'll show you the scale in a second. Some of the best models right now are run at basically 10 kilometer resolution. So this is Manhattan. And you're going to see what a grid box of a really high resolution model look like. So it's going to be 0.1 degree by 0.1 degree horizontally. And you're going to see all those little boxes. And we're going to solve the equations of motions and the thermodynamics in each one of those boxes in those 10 kilometer by 10 kilometer resolution. And so here what we're seeing is the surface temperature in this climate model. But that's a very high resolution model. And we can't really afford that. And that's still quite cost, right? It's 10 kilometer by 10 kilometer. And you can see we basically kind of wiped out Manhattan within that grid box. So you can't get any resolution in that. Now, that's what climate models look like in general. So that's the simulation I showed you before with a 10 kilometer by 10 kilometer grid box. Climate simulation usually looks something like this. They're usually 100 kilometer by 100 kilometer resolution. You can see it's a lot more sluggish. Some of the current simulation are 40 kilometer by 40 kilometer roughly. But again, right, so the more you increase the resolution, so the finer you make the grid box sizes, the more of them you have, the more expensive it is to actually run your simulations. So those very high resolution, we can run them, but only for a few years. And most modeling centers are very constrained by basically the ability to run them for a long time. So that's why we're stuck in this world that is more sluggish, a bit more viscous, doesn't really look like the turbulent flow that you see here. And that means you make your projections a little less true, a little less real. It captures the right effect, but we have some uncertainty because some of those processes are not well captured. And so that's what we call uncertainty in climate projections. Because many of the things that are happening below the grid box size of the models are too small to be represented. And what I'm talking about are clouds, right, which you see all the time. Those are much, much smaller than the grid box size of a climate model. So we need to come up with some basic, representation of them in our equation. Other things are, sea ice interaction. Again, usually those processes are much smaller. And in the ocean, mixing and turbulence. All of those things are much smaller than the grid box size of a climate model. That means we can't resolve them directly. The other uncertainty in climate projection is the fact that, well, we took, for those of you who are familiar, we took equations that we call our continuous. And then we need to break them down into pieces and solve them on the grid. That means we're going to take a derivative that is continuous and nice and beautiful. And for those of us who love math and physics, we know how to solve. But down a grid, then you need to make some approximation. And those approximations introduce errors. So those two components, the fact that we have processes in climate models that we cannot resolve, but are critical for climate, and the fact that we need to make approximation as we solve them on the grid, those two things leads to uncertainty in projections. And even though you give your climate model the same scenario for the future, it might give you a different answer or slightly different answer. I just want to make it clear. We still understand that the climate is going to warm, that sea level is going to go up. We have a very good physical understanding of that. But there is some uncertainty around the numbers. So for decades, what we've done is come up with simple mathematical models that say we'll represent clouds or we'll represent how the ocean mix, and we come up with simple equations. And we put them on the right-hand side of our climate model and to represent the effect of clouds on the climate or the effect of mixing on the temperature. And, we've been doing that for many years and it's been successful, but I show you, we struggle. We struggle because we have some uncertainty. So my recent work, and it was mentioned, earlier that, we've been dabbling with machine learning or artificial intelligence. So actually trying to solve that problem, and rather than make assumption about what the physics should look like of those processes we can resolve, why not use the data? Why not ask, the algorithm to actually pick out the best relationship between, say, ocean mixings and temperature? So I don't want to replace the full climate model, to be clear, because I have equations I love and I know them and I understand them. But then there's these little things that I don't resolve, again, like clouds or ocean mixing, where I could learn their representation from data to just enhance my climate model and try to reduce that uncertainty to make it more physical. And so that's what we've been doing. We've been using some of the high resolution simulation I showed you before. We have a few of them. Again, we can't run them for long, but they generate a lot of data and they can show me all those processes of mixings and clouds, and then use machine learning algorithm that we constrain with physics because there are still laws of physics that need to be obeyed. And we ask the algorithm, okay, I don't want to just tell you, what the answer should be, what a mathematical model should be for turbulence. Take the data, take the algorithm with some physical constraints, and then come up, for me, with a good representation of what those processes should look like. So then I can go and add them to my climate model, in addition to the full set of equations that I already have. So people have been doing that for the atmosphere. My group has been doing that for the ocean for a few years now. And I'll show you some of the successes and some of the challenges. So I'm extremely grateful for the support of Schmidt Futures. So I'm leading an international collaboration to actually try to take those ideas and learn, with scientific machine learning, what we call parameterization or closure, so representation of those small scale processes that are not captured in climate models. So, and our goal is, of course, to improve climate models, to improve climate projections. It's really a blend of, data, physics, and scientific machine learning together. With 30 scientists now, so it's really exciting. Many of us are experts in climate, so and that means, we have domain knowledge of atmospheric dynamics, ocean dynamics, sea ice dynamics. We have experts in machine learning, so really people who actually, design those things and understand the theory of machine learning. And we have climate model developers, so people who actually build the climate models. And so it's been a very exciting adventure. We started during COVID, so it's been an interesting challenge for me to lead a team of scientists, between the US and France and many institutions, but it's been wonderful because we've been doing a lot of fun stuff. And so really what we're going after is using physics, machine learning, to actually learn processes like convection in the atmosphere and how cloud will impact temperature, how mixing in the ocean happens and transport temperature and so on and so forth. So it's a big challenge, of course. You can always apply machine learning to something, but you want to be careful. You don't want to apply it just to apply it and you get something magic. But then at the end of the day, we need to take all those processes and then put them into climate models and then hope for better predictions. So I'll show you a couple of things that we've been doing for ocean turbulence, and then I'll close there. So just an example. So again, as I mentioned, ocean mixing is not resolved in the current generation of climate model. So we're interrogating machine learning, which are called convolutional neural networks. So usually they're pretty good at predicting images. You're giving them images and they tell you if it's a dog or a cat. Except in our case, we're asking it to come up with representation of ocean turbulence in physics. And so we've been doing that by taking data from high resolution model and asking the neural network to predict what is the missing mixing in climate models, or what is the missing representation of mixing in climate models, just given that data set. And to be honest, I was shocked because I was a bit of a skeptic at the beginning. I did an amazing job. So what I'm showing you here is the skill of the prediction. And what I mean by skill is basically how well the prediction works for capturing this ocean mixing based on data. So when it's, kind of brownish, that means that it's basically perfect. When it's blue, it's imperfect, but it's still 50% there, which is usually better than the old approximation and mathematical operators we've been using. And in the majority of the planet, the skill, again, the prediction, is more than 70% correct. So really just based on data. Some places where it does poorly, it's up here, right? So, in the high latitudes, and that's usually where ice is happening. And one reason is, well, we didn't give the algorithm anything about the interaction with sea ice. So it does not know that physics because it's never seen it. So that shows you some of the challenges. You need good data for the processes you're trying to learn. When you don't have good data, you don't get a good prediction. So even though it's, you might think that you can learn anything out of anything, you can't. The reason it does a good job is because it was able to capture the right physics given the right data. Now, the problem is I'm a physicist. I understand broadly what it does, but I don't really, because that algorithm gives me a prediction with thousands of parameters. And so it's really hard to, unpack what it learned, even though there are techniques, but yet they've been kind of falling short. So we come up with a different idea, which is I understand equations, just, based on my training. So algorithm now, what they can do is they actually, if you give them data, they can also try to learn an equation for you. And what I mean by that is you still give the algorithm a data set, but you give it, different operations given that data set. And so now we, again, give the algorithm some data and we ask it the same question. Give me an answer for what the ocean mixing, should look like. And so we give it a set of basis function, a set of equations, and it's basically going to go and select the one that will mimic the best the representation of ocean mixing. For those of you who can see that, it's kind of a nice symmetric stress tensor. And the beauty of it is we could explain every piece of it at the end, and it's related to some old theory of turbulence. And so really now the algorithm actually pick out a set of equation and we can go and actually explain every piece of that equation. And of course, again, it's kind of simple and beautiful and you can explain a lot of physics out of that. So you learn new physics for the representation of all those missing processes. So machine learning is not just a black box, can help you, or at least unravel some pieces of the dynamics we didn't know before. So of course, putting that into climate model is not an easy task, and it's going to take us years. But what we do is simulation in very idealized setups. And I'm not going to explain that very much, but usually you have a high resolution model that you're trying to mimic, and that's the currents. That's the coarse resolution model, and you can see the currents are weaker, there's less variability, there's less wobble, right? There's not as much structure as here. Now, if we take this model and we enhance it by adding those representations that I just talked to you about, just using the part that the machine learning has learned, we just add a force on the right-hand side of the equation. We're not replacing the full equation, we just add a force. That's the one that comes from the equation we discover. And that's the one that comes from the neural network, which is kind of this a little bit of a black box. In both instances, it looks a lot more like the high resolution than before without the computational cost. And so that's a big improvement for us, that by adding this new term that we learn directly from data with some physics constraint, we can make a coarse resolution model that, if you remember, is blurry and kind of viscous, gives me a lot of uncertainty, look like a high resolution model where it represents all the processes, but without a computational cost. So that's a big advantage for us. This is a very simple simulation, and now we're trying to actually put that into real climate models. So just want to conclude with 2 slides by first thanking all of you again and KITP for the wonderful time. So we've been running a program since November 1st. It's called Machine Learning and the Physics of Climate, and really has been trying to touch on all those challenges that I told you before, right? Quantifying changes, and the fact that we have sparse data, that it's hard to understand, but we have good equations. Trying to understand how this planet is changing and trying to improve climate models. And so bringing physicists, with experts in stats and machine learning has been a wonderful experience. And already we came up with so many great ideas, and that's kind of the blackboard from, a couple of weeks ago, just before Thanksgiving, where we actually laid out a couple of problems, and I already started working with 6 people that I've never met before, in some new challenges to improve climate models in a way, again, that I've never thought before. And so it's been an absolute, fantastic experience. As a scientist, it's like being a kid in a candy store, that you're in a place where you're immersed with amazing scientists, where everybody is excited to learn new things and work on new projects. So I'm going to leave you with a few thoughts, my own. Oceans are an essential component of the climate system. As I mentioned, it absorbs a vast majority of the heat and carbon in the system. They've been warming for decades, and they will continue to warm, and that will affect sea level, storms, as mentioned before, right? We're fueling the storms as the planet are warming, and we know that from many things. We know it from physics, we know it from observations, and from models. Climate models have been, again, amazing at predicting the mean response to forcing, but they still have some imperfection because we don't have the computational power to actually resolve every single process all the way down to the molecular scale. And so that remains a challenge, but we have emerging tools as long as we combine the right way, physics, computer science, and emerging tools. And that's always important to keep physics at the core of it. We don't want a black box. We really want to combine the right physics with the right tools. I always say, challenges are opportunities for us, and there are many of them ahead. And so I think there's a lot of exciting time coming for us in improving our understanding of the climate system, the physics of it, and making better predictions. And so again, I'm very grateful for the support of, our funders, NSF-NOAA, Schmidt Futures, Volo, and of course, KITP again for absolutely a fantastic time. Thank you all very much.
Okay. So going back to the slides where you showed the computational fluid dynamics, cell size resolution, and that can't do it all, right? That's why you wanted to improve the numerical solutions of the set of partial difference equations like the Navier-Stokes.
Exactly.
And you've gone to AI. You've given it over to that, but isn't there a danger there because you've given up physical insight and you're predicting out 50, 60 years. So isn't that a problem?
Yeah, absolutely right. And I think this is a critical point. We do not want to learn something where we completely ignore the physics. And that's why I kind of love this, then maybe I'm completely biased because it's our own work, but that's why I love this part, Well, now, rather than saying, oh, I know exactly what it's going to be, the mathematical representation for ocean mixing, I'm learning it from data. And then I end up with an equation where I can actually get my physical insight from it directly. And so it's a little bit different than the way we've been traditionally doing it, saying, oh, if I take a cup of coffee, I put some milk, I'm going to mix it. Mathematically, I could write that as the Laplacian of something, right? Roughly will do it. Now, I'm not making that assumption. I'm saying, okay, I'm giving you the data. I'm showing you how the turbulence is evolving. And I'm asking the algorithm to come up with an equation. And then when I get the equation, I crack the books and I go and I try to understand how this tensor works. And that's how we get the physical insight. That's an extremely important point, to not throw away the physics. This is what we, this is what we live for. Thanks for that. Yeah, this is very important.
That was a great talk. Thank you so much. Can you go back to the slide that showed the excess heating in the Atlantic? And yeah,
it's a good one. Huh? It's a good one. Yeah.
Really
I love it.
To a lot of people. So that was. So thinking about this from really simple like 2D heat transport. If I were thinking about like heating in a semiconductor device or something like that, I would think that a heat buildup like that comes from two causes. One, a non-uniform generation of heat, and then two, constrictions that prevent the equilibration on the timescales that you're looking at. So the constrictions are pretty obvious geographically, but where, assuming my assessment is correct, where is the non-uniform heat generation coming from?
Yeah, excellent question. And so your intuition is spot on. Part of it, non-uniform heating at the surface. Second part, construction, as you said, continental, but also from the forcing. So the wind over here, over the Southern Ocean, is very different than the wind in other places. And that generates a net transport northward. And so then you're going to add a lot of heat building up in the Southern Ocean. And so that's part of it. It's not even necessarily because of the continent. It's just because we've got a wind that actually blows all the way around and creates a net transport north. Then the second part here, so in general, we have a circulation that moves heat from this low latitude north. But the problem, what happened, is that a lot of the circulation has been decelerating. So now it's building up a lot of heat over here. And it's mostly located in the western boundary because that's where the currents are. And up here, some of it is being actually taking up at high latitude and then moving south more slowly. So you've got all those pieces coming together of the circulation moving things around, again, kind of this dye that get absorbed and kind of get basically kind of moved into the interior, but some of it is getting slower and again basically being piled up because you heat more and it doesn't move away as fast.
So primarily circulation generated, not non-uniformity in the generation.
A bit of both, actually. It's kind of a bit of both because they're so coupled. As soon as the temperature changes at the surface of the ocean, the atmosphere disequilibrium is changing. That means your forcing is changing as well. That's the mess of the climate system. You remember the first quote? Doesn't matter how complicated a model looks like, it'll become more complicated the more you look at it.
Yeah, I basically had the same question as Craig, but I also had a follow-on, which sounds really horrible, which is there any possibility of geoengineering to buy any time?
Yes, and yes, and so a lot of people are thinking about this, right? How to geoengineer the planet. Multiple solutions are being discussed, but very quickly we figure out that you might do more harm than good. So I'm believing people. I believe that we see the planet is changing, and the more CO2 we're emitting, the more the planet is warming, and so I believe in the collective of people that we will change how much we're emitting and how we're emitting and how we're burning fossil fuel. I hope we don't get to geoengineering. I'm afraid some solutions will have to be taken, but I still believe that we can change the course in a different way, at least before. Maybe I'm too hopeful.
Hello, thank you. Great lecture.
Thank you.
Are you saying the deeper, colder currents are slowing down or being blocked, or is that's basically what's happening? That's why it's not getting the heat out.
Yeah, so part of the currents have been slowing down. Now, so in the observation, in what we've been observing, it's not obvious that it's because of climate change. Some of it can be natural variability. In the future projections, what we see is that the circulation is decelerating, and that's why we get this kind of accumulation of heat, and that would be because of climate change.
Thank
At
you.
least in the numerical simulation. Yeah, thank you for the questions.
Okay, well, I think if you had a logo for this talk, it's obviously this slide. All right. Thanks, everybody, for coming.